this is given to researchers around the globe, and then what it means is that we will need a host institution, for example, and then we need an American, professor, if you like, or a scholar to come and be with us and give us some mentorship. Basically, I think that is our solution. And so for our group, we are led by Professor Patrick F. Mensah. I'm going to try to introduce him proper. Yeah, Professor Patrick F. Mensah is here with us. He's the fellow from the Diaspora from the United States. Let me tell you, the seat of the Andrew Carnegie Award is also from the United States. So I guess they need proper supervision, therefore they bring somebody from there to come and be with us. But I am hosting. Is it okay to say that we got the grant, and then the co-host is Dr. Asiedu. So that is why Prof is here. And as part of our preparations and work, which is centered on cloud microphysics and aerosol pollution simulation. Basically, we want to see how aerosols and other particles in the atmosphere affect cloud formation and rain and all that. And almost all of you here, across engineering and from the sciences, will bear with me that we try to look at these things because of climate change and so on and so forth. Acid rains, greenhouse gases emissions and all that, even though that's a bit far-fetched, they are all in there in the mix. So that is why Prof is here. And so, under the auspices, of the College of Science, because Dr. Asilevi Jr. Is a lecturer at the Department of Meteorology and Climate Science. Yes, from, I don't want to say physics because that's different, but it's around physics. Okay, so because they are also part, this is under the auspices of the College of Science and College of Engineering. And so we have the Department of Meteorology and Climate Science and Department of Chemical Engineering primarily trying to host this. And as part of this, we have to take a crash course because we have to speedily do this thing within a space of about 3 days, if you like. The regular fluid transport we have done, we took it a whole semester, but we are trying to see how we can crash this and get some for the purposes of what we have to do. Sometime later, we will be looking at density functional theory, not part of this crash course. You guys need to remind me so that I make that also happen. But this is on computational fluid dynamics, and then we'll try to see how it goes. So, ladies and gentlemen, at this juncture, I would like to introduce Prof by just mentioning a few of his expertise or what he's looking at so that you know what he's into. Professor Patrick F. Mensah is a professor and a Formosa, that word I tried to, Formosa, see? Formosa endowed professor and associate dean for research, Southern University, Baton Rouge, okay? And then his specialization is in experimental and computational fluid and heat transfer. We are safe, okay? And then his expertise cut across modeling, processing, and thermomechanical property characterization of composite materials, high temperature, super alloys, and ceramic thermal barrier coatings. His education, he has a PhD in engineering science from Louisiana State University. That was in 1998, right? He's too handsome to have completed PhD in 1998 and have this look his have. His research, his ongoing research in his group is supported by CIMM, that I don't know, which focuses on developing computational heat transfer models for analysis of multi-phase heat transfer in microscale heat sinks manufactured by metal form. Wow. Then he looks at numerical modeling and simulation approaches for analyzing additive manufacturing, AM, processes of metal powders involving lasers as input heat sources, is also under development. AM, that I mentioned earlier, which is additive manufacturing, produce parts through the layer by layer addition of molten material that generates large temperature gradients that cause plastic deformation. Thermomechanical models predict thermal history, mechanical distortion due interfacial thermal stresses. This enables the process to be steady and for distortion mitigation techniques to be developed. Such investigations require models that accurately capture the physics of the deposition processes. Ladies and gentlemen, I think that this is a bit too technical for our other audience who may be from different faculty. But trust me, I know that you are safe, because most of you are going to take material science engineering with me. Most of these ingredients are there. So we'll be safe. At this juncture, with a mighty hands of applause, let us welcome Professor Patrick F. Mensah.
Well, Dr. Kwaku, thanks for the kind introduction. I would like, at this juncture, just to make some slight modification, because what he read on my bio is from years back, when I was working on the Consortium of Innovation and Manufacturing and Materials project. That stands SIM. And since then, we have moved on to working on the Louisiana Materials Design Alliance, also focusing on composite additive manufacturing of metal-based additive manufacturing, as well as polymer-based additive manufacturing. And I'm no longer serving as an associate dean, but I serve as a senior associate vice chancellor for academic affairs at this institution. And so today I am going to give you a crash course, the introduction to a crash course in fluid dynamics. As the name implies, it has a computational approach to solving fluid dynamics problems. Before I move on ahead, I just want to get an idea of all your backgrounds. So let's start. How many of you have taken at least all mathematics up to differential equations? All right. So when we say an ordinary differential equation, you know what an ordinary differential equation is, right? Yes. Okay. But what is a partial differential equation? One person. No, I want to see. What is a partial differential equation? I thought you said you've taken all levels of calculus. Yes. And please introduce yourself when you get up, okay? Nana Kojo. Okay, Nana Kojo, go ahead. Okay, you take the partial differential of a function that is multivariate, okay, as more than one variable. Okay, so you would see that, you know, in fluid dynamics, well, let me ask my next question. How many of you have taken fluid dynamics? Okay, so at least before taking fluid dynamics, all right. How many of you have taken heat transfer or are now taking heat transfer? Okay, so you are all smart. So this would be what we say easy peasy for you or cocoa for you, okay?
You don't raise your answer.
All right, so traditionally, this is really a graduate level course. Okay, this is a graduate level course. And as defined above, it involves advanced numerical methods for solving the Navier-Stokes equations, numerical solutions to a boundary layer problems, solution of potential flows, and computational heat transfer. Now, how many of you have taken a numerical analysis course? So you see that what we are going to do is actually the application of what we learned in numerical methods, okay? Numerical method is just, you have an algebraic set of equations and you use a methodology such as the Gauss-Seidel or the Thomas algorithm, if you remember, or other tri-diagonal matrix systems to solve that numerical problem, okay, to obtain the solution. Well, basically what we are saying that in fluid dynamics, we have our governing equations that form the fluid dynamics, right? We are going to cast them in a form that will be solved numerically instead of obtaining exact solutions for a number of different cases. I don't have a textbook. Well, I have one book here with me, okay? But for references, if you go back home, or you go back to your dormitories or your apartments, these are some of the textbooks that you can reference, okay, for what I'm going to talk about. Okay? These are all books that you can reference for what I'm going to talk about. In fact, the background of, or I should say one of the fathers of computational heat transfer is Professor Suhas Patanka, whose finite volume approach has been the basis for the Fluent ANSYS CFD software. I asked you questions about your background. So you see that some of the prerequisites to fully understanding the CFD course involves vector differential calculus, the basic knowledge of fundamental fluid dynamics, okay? Understanding of the application of conservation of mass and momentum in fluid flow systems, understanding of the application of conservation of energy in thermal systems, okay? That is why I asked about your background, okay? So since you informed me that you've taken all these courses, I know that you are well prepared and I do not need to go back to the time when you were teaching these courses. However, if you have any questions at any point during this lecture discussions, of course, raise your hands and ask the question. The overall objectives are to demonstrate through report writing, oral presentation, and proposal development skills through projects that will be offered in the class. Well, yes, in our graduate level course, we expect you to do some project at the end where you would present what you've done pertaining to this course, that is the computational fluid dynamics. I'm not going to expect that of you, okay? But I'll be giving you assignments. You should be able to categorize partial differential equations as either elliptic, parabolic, or hyperbolic, okay? You should be able to solve numerically It's back? Okay. You should be able to solve numerically the governing partial differential equation for any flow problem, whether it's in 2D or even in 3D, okay? Know the solution process of CFD problem in general, okay? Well, we don't have a license for the ANSYS software here, I'll make references to it. But knowing what you know from what we are going to go through here, that should give you a firm understanding of what takes place in the background when you are using softwares such as ANSYS, COMSOL, FlowBench, and other softwares that are used to solving CFD-related problems, okay? So at the end of the day, you should be able to develop problem-solving skills in CFD through continual testing and problem assignments. Now, Dr. Boakye indicated that, you know, within our Carnegie funded project, we are going to work on how aerosols impact the climate, okay? Impacts the environment. Well, you see, I'm also doing continual problem solving and learning because through this project, it's giving me the ability, or it's giving me the opportunity to basically apply my CFD background to his climate science. Traditionally, I have applied my CFD background in the solution of materials-related problems in heat transfer and also in fluid-related problems in multi-phase flow, okay? So, you know, the expectation is that this is not be the end-all or, you know, after we go through the process, but it will give you the ability to basically keep learning, okay? A lifelong learning process. This is typically what we would capture or go through in a given semester. We are going to start over here, do the general introduction of CFD. We will also go through the solution procedure, a beginning governing equations for CFD. We'll talk about some of the mathematical implications and go as far as we can in this presentation within this next 3 days. Okay, so let's start. Now, this is where we really start this course. The phases of fluid mechanics. How many of you have heard about Archimedes? Yes, tell us something about Archimedes. Yes, what do you know about Archimedes? What is the Archimedes principle? Okay. A mass displaces an amount of fluid equal to its volume, right? How about Newton? What do we know about Newton? Okay, laws of motion and what? Yes, Nana? He invented calculus. What else? Okay, gravitation. Remember, F is equal to ma. Okay?
Prof.
Yeah.
Okay, so Asiedu now. So at the end of this crash course, you are going to be given certificates, really. You will be given certificates for us. So please, put on your thinking cap. I trust in you. So let's move on. Newton, yes.
Okay. Newton-Raphson method, numerical analysis. Okay. Leibniz. We are getting into deep calculus. Okay. Bernoulli. We've taken fluids, right? We've heard of the Bernoulli equation. Euler, also in fluids, okay? And so on and so forth, okay? All these great men have impacted the subject of fluid mechanics, okay? It is on their work that the subject of computational fluid mechanics has been developed based on the governing equations and the mathematical formulations that they came up with. Okay, so when you see all these men here, hopefully someday, your picture would also be displayed as coming up with something that contributes to the subject of fluid mechanics. Okay? At the end of this first series of lecture on computational fluid dynamics, I want you to understand what is fluid dynamics, computational fluid dynamics, why is it important, okay, and where it can be applied, okay, the what, why, and where. Okay, in fact, I have an assignment for you to go back and research online various areas of applications when you are after this first lecture. Okay? I want you to understand what we mean by modeling. Okay? And you said you've taken numerical methods. I want you to understand how numerical methods impact computational fluid dynamics. Okay? Have some familiarity with computational fluid dynamics codes, what we mean by the CFD process, and finally, an example of CFD process. Okay, so let's turn to the first bullet, that is the what, why, and where. So CFD, in essence, uses mathematical formulations. Okay, we use mathematical formulations for a physical problem, and we simulate it using numerical methods. What are the numerical methods? Discretizing methods, using numerical solvers, using numerical parameters, using grid generations, and so on. Okay, so CFD in general is the simulation of fluids engineering systems using numerical methods. Historically, we've used analytical fluid dynamics. That means that you have the governing equation for fluids, and you can obtain exact solutions, such as coming up with a simplified form of the Bernoulli equation that you can use to determine, for example, what? What can you use the Bernoulli equation to determine? Pressure drop in a pipeline, right? Okay? We can use the Bernoulli equation to even model the speed of the fluid at the exit, or calculate the speed of the fluid at any point along the pipe. Okay? We've done this analytically, but we can also do it using computational simulation. Okay? The other approach, of course, would be to do it experimentally. Okay? The other approach would be to do it experimentally. If we can do it historically by analytical fluids and experimental fluids, then why is there a need for CFD? Okay, why is there a need for CFD? Anyone? Yes, please introduce yourself. Okay. That's an excellent, excellent answer. Okay? On the analytical solution side, it's not every problem that you can come up with a closed form analytical solution. Okay? Particularly if the problem has non-linearities in it. Okay? Solving the differential equations to come up with exact solutions is very complicated. On the experimental side, it can be cost prohibitive to build a big experimental system to basically characterize or solve a problem. However, if you can use computers to simulate it, that will save time and that will save you on the cost. So particularly, CFD has been made possible by the advent of the digital computing, okay, and advancing improvements in computer systems. So why we use CFD? We use CFD for analysis as well as design. And I would also add here, right now, also for education. Okay? Now, in your fluids class, did you undertake any experiments? Did you undertake any lab? In your fluids class, did you do any laboratory work? No? You did pressure drop across pipe. You did some experiments, right? Now, you can do all of that. So when I say education, we can use we can use computational fluid dynamics to teach you the pressure drop in a pipe. We can use computational fluid dynamics for you to visualize what we mean by when we say, oh, there is laminar flow in a pipe. Okay? Or there is turbulent flow in a pipe. Okay? Seeing is believing, right? So we can use CFD to visualize that. Okay? So it helps us analyze and it helps us design more cost-effective and more rapid than experimental fluid dynamics. CFD provides high-fidelity database for diagnosing flow field. Okay? 2, simulation of physical fluid phenomena that are difficult for experiments. Well, full-scale simulations. Imagine you have to design a new ship, okay, or design a new aircraft. And as part of the work as an engineer, you have to determine the lift forces, the drag forces, the aerodynamic forces on the ship, okay, on the ship submerged in the sea, in water. You still have to analyze the hydro forces on the ship. Okay, we can do those full-scale simulations using CFD. Body layer, stellar evolution, all of that can be modeled using CFD. Now, the other part of this is also using other computational simulation means that Dr. Boakye also alluded to when he mentioned density functional theory. Okay, that has more applications in the physics. So we use CFD knowledge and exploration to really understand the flow physics pertaining to various engineering applications, both in the analysis and design. So let us look at some specific examples of where CFD is used. Aerospace engineering. We look at this F-18 jet warplane, fighter aircraft, okay? The release of these missiles that are attached to it, okay? The impact forces, or even the wake around the aircraft as it impacts other fighters in its vicinity, all can be analyzed by CFD. Okay? In the design of the aircraft, not only are we looking at the aerodynamics around it and also looking at the lift forces, but we're also trying to mitigate or to come up with the control systems that impact various applications or that impact various problems that the plane may encounter. In the automotive industry, now you see all sorts of fancy cars that are now being designed. Okay? A long time ago, we just needed a transportation that moved. So they just designed a box system and put an engine to it, and it moves. Okay? It takes us from point A to point B. Now, in the racing industry, we've heard about Formula One racing, right? In Formula One racing, well, the aerodynamics of the automobile, of the race car becomes very important. Okay? And so we need to design the car such that we will reduce the drag forces on the car and make it go very fast. Okay? Not only do we use CFD for the external features of the car, even the combustion, okay, in the engine, in the internal combustion engine, the intake and the exhaust from the combustion pistons can all be analyzed using CFD. In biomedical applications, here you have temperature and natural convection currents in the eye following laser surgery. Now, to do cataract surgery, a long time ago in cataract surgery, they will have to cut the lens from your eye carefully to do that surgery. Okay? Now they can do it with a laser, which is more precision. But then the question is, how does the heat input from the laser impact your eye? Impact the blood vessels of your eye? Okay? That can all be analyzed using CFD. Okay? Or even the flow or transport of drugs within blood vessels. Okay? That can all be analyzed using CFD. So CFD now has a wide application in biomedical applications. In chemical processing, okay, this is a schematic of a polymerization reactor vessel, and in it you can predict the flow and separation of the resident time effects within this system. Okay, in the process industry, when you have heat exchangers, okay, you can basically use CFD to characterize the heat exchange between various fluids during the process. In the design of buildings, when you want to look at the impact of these air conditioning systems, okay, you can use CFD to analyze the flow of the air conditioning in the room and see how it affects the temperature in the room so that we, the occupants, can be comfortable. Okay, in hydraulics, okay, such as this scored downstream of a flood control system. Just imagine that you have the Akosombo Dam, okay, and the floodgates are open such that downstream it basically flows uncontrolled. It would impact the environment, or it would impact the inhabitants downstream. How do we make sure that we carefully open these floodgates such that you don't cause havoc downstream? Okay, so again, we can use CFD to analyze open channel flows. Okay, in hydraulics, you can use CFD to analyze the flow of oil. We have petroleum engineers here, right? Okay, we can use CFD to analyze the flow of oil or the flow of gases within pipes. Let's move on to the next. Okay, so here in the marine, okay, so in the marine environment, you have this body basically in the marine environment, and you want to basically analyze the forces, the drag motion of the object submerged in the water. Okay, why is that important? Because the deeper you go, the higher the pressure forces that you have, right? And so you want to be able to characterize whether maybe am I using the right materials for this marine structure, such that as I go down deep into the water, it is not basically compressed and collapsed. Oil and gas industry, we look at this drill bit. Okay, we look at this drill bit. Can we characterize the flow of lubrication mud over the drill bit? Okay, we can use CFD to do that. In power generations, where you are also releasing a lot of, here from the cooling tower flows to the environment, how does the release impact the environment in the vicinity? You can use CFD to analyze that. This is an American football, okay? And we can use CFD to look at the aerodynamics in sports. This is football. It could be regular soccer ball. It could be golf balls, and so forth. Any comments or questions about the what, why of CFDs and how it's used? Yes?
For the sake of those of us from the atmospheric environment, if you could throw some light on CFD application in atmospheric science.
Okay, that's a very good point. And remember, you have a homework problem. I'm giving you some examples here. I want you to go back, research, and come up with additional examples as we learn. Okay? So in the atmospheric realm, okay, when you want to do a lot of climate predictions, just imagine all the cars that you have in a given area. Because of the emissions from the car, you can have smog in your environment, okay? And so the question is, how does the concentration of these emissions impact the climate or the weather in the environment? Okay, we can use CFD to analyze that. So long as we do understand, okay, all that this boils down to is understanding what are the governing equations to apply to a given scenario. Okay, and what are your boundary conditions, as we'll see later on in applying to a given scenario. Okay, does the problem in doing the CFD analysis involves any chemical reaction or not? Okay. More questions or comments? More questions or comments? Prof, did I answer your question?
Yes.
Okay.
I think even earlier, in the previous slide or so, you mentioned emissions or
Right. Yeah. So here, the environmental effects and the hazards. Okay, pollution. Well, what causes pollution? Pollution can be caused by emissions from chemical plants. Okay, whether the chemical plant is producing, releasing a lot of sulfur to the environment. Okay, the environmental plant, the plant, or like I said, traffic, your vehicles is producing a lot of nitrogen oxide or carbon monoxide to the environment, and so on and so forth. All of that basically can be analyzed using CFD. Okay, so now we move on to what we mean by modeling, okay? We now understand what we mean by various examples of CFD, but to really do computational fluid dynamics, you have to take the first step. You have to model the problem using mathematical formulations, okay? Using mathematical formulations in terms of initial boundary value problem. Okay, but what is an initial boundary value problem? Well, the initial boundary value problem is a form of a partial differential equations with appropriate or with supporting boundary and initial conditions. In order to do the CFD analysis for flow, for the aerodynamics over an automobile, we need to come up with a mathematical formulation of the fluid flow over the car. And so you apply the conservation of mass, the conservation of momentum over the car. You will have to apply a boundary conditions. How do I apply the boundary conditions? Well, you have to have a region in space where you're going to do that analysis. Does the problem involve initial conditions? In other words, at time zero, what is the environmental condition? Is everything stagnant? Is it raining? Okay. Is the temperature very high? Or are we at room temperature? If I want to do a CFD analysis as a result of superimposing these air conditioning systems in this room, we need to start out with a situation where, well, the temperature, there's no air conditioning in this room, and so the temperature is high, above 21 degrees Celsius. Now, then put in the air conditioning system, turn it on, the air conditioning system is set at, say, 17 degrees C. How does the temperature in this room basically vary with time? How long does it take for the temperature of this room to reach a comfortable temperature for the inhabitants? Okay, so that is what we mean by initial value problem. Okay, what is the initial state of your system, and what are the boundary conditions that impact the solution of the differential equation? Now, in modeling in CFD, this includes first understanding of your geometry and your domain where you are going to solve the problem. Okay? You have to know your geometry and the region or the place, the area that you are going to solve the problem. You have to understand what coordinate system to use. Okay? You have to understand what coordinate systems to use. You have to understand the governing equations that you have to use or you have to apply. You have to understand the flow conditions. You have to understand or know the initial boundary conditions, and then the selection of models for different applications. So every CFD problem will have a pertinent model that is germane to it, that can be applied to it. Let's look further into the geometry and the domain. Simple geometries can easily be created by a few geometric parameters. For example, if you have a pipe, okay, if you are analyzing flow in a pipe, what coordinate system do you think you have to solve the problem in? Cylindrical, right? So if you recall, when you were taking your fluid dynamics, when you are solving pipe flow problems, you use the cylindrical coordinates to solve the pipe flow problem in determining the pressure drop. Okay? On the other hand, if you have a rectangular channel instead of a circular pipe, if you have a rectangular channel, then you would use rectangular coordinate system in order to solve the problem. Okay? Now, you can also have complex geometries. These must be created by partial differential equations, or, as in today, using 3D scanning or importing database of the geometry, e.g. the effort, into a commercial software. Now, what do I mean by this? A pipe is an easy system to represent, right? What if within you want to analyze the heat transfer of the electronic chips in your computer? Okay? How are you going to do that? You see, in CFD, we always have to come up with a geometry. That geometry requires us to be able to represent it pictorially using a drawing. Okay? In some cases, yeah, you can just use straight lines to represent it. In some cases, you have to use really curved, complicated structures. If I take a look at this speaker,
line in.
if I take a look at this speaker, if I'm to draw it, it's a complicated structure, okay? But now, thanks to technology, we can use a 3D scanner to scan the object and then import it into a commercial software, and instead of you, the engineer, using your drafting techniques to really draft it, okay? That is why, at least in the US, we've stopped teaching drafting, okay? Because you can easily create objects using various softwares and also using 3D scanning techniques. Okay, you scan. My whole body can be scanned such that it's imported into the software, and they can do CFD of my body mass of my body mass. Okay, that's what I mean by complex geometries. Okay. And of course, you have to have a firm understanding of the size and the domain. Are we doing the CFD over a prototype car, an entire car? Are we doing the CFD over a bus? Are we doing the climate weather analysis over the whole of Kumasi or over the whole of Ghana? Okay? That domain and size becomes important because that impacts your computational resources. Okay, so here are typical approaches that are used in geometry and domain analysis. We do a lot of geometrical approximations. We use computer-aided design and computer-aided engineering integration software. So these are some of the softwares, including AutoCAD, including Solid Edge, okay, and other softwares in order to generate the computer-aided geometry of the object. And then we have to have an understanding of whether we are going to use the Cartesian coordinate system, of course, the rectangular coordinate system in X, Y, or Z, the cylindrical coordinate system in the radius, the circumferential angle, or the axial distance Z, or the spherical coordinate system, again, the radius, circumferential, or azimuthal angle phi. One has to choose the appropriate coordinates to solve the problem. Okay, so this is just giving you a breakdown of what I mean by the different coordinate system. So in other words, if I'm solving the problem in the Cartesian coordinate system, then my governing equations have to be written in the Cartesian coordinate system. If I'm solving the problem in cylindrical coordinate system, then the governing equations has to be transformed into a cylindrical coordinate system. If I'm solving a spherical coordinate, if I'm solving the problem in spherical coordinate system, then the governing equations has to be transformed into a spherical coordinate system. So, question. You want to analyze the temperature as well as the pressure forces in a storage tank. Okay? How many types of storage tanks can we have? Anyone? How many different types of storage tanks configuration can you design? Okay, your water storage tank, how would you classify that? Cylindrical, right? Okay. Or your storage tank can also be rectangular. Okay. In a lot of process industry, you also have spherical tanks. Okay. So this is what I mean. Depending on the nature of the problem, we can either use, if it's a rectangular tank, then we are going to use the Cartesian coordinate system. If it's a cylindrical tank, then we are going to use the cylindrical coordinate system or spherical coordinate system. Okay? So you have to really have a firm grasp as to the geometry of your problem in CFD as you design it. Okay? And in some cases, there may be some coordinate transformations that may be required. Now, how many of you have seen these equations before? Do you remember them? Okay, so when you see, in the beginning, I gave you the pictures of a lot of famous scientists, right? Well, two famous scientists, Navier and Stokes, came up with these equations. Okay? Later on, I'm going to derive them for you, okay? But for now, I basically present to you the three-dimensional Cartesian coordinates representation of the Navier-Stokes equations. The first equation basically represents the equation in the x direction. The second equation represents the Navier-Stokes equation in the y direction. And the third equation basically represents the equation in the z direction. I mean, they all look similar apart from the fact that you have a u term on top and a v term here in this second equation, and a W term here. What is the significance of U, V, and W? What is the significance? What is the significance of saying that, well, this is a representation of the Navier-Stokes equation in the x direction? What is the significance of U in this equation? Now, Navier-Stokes equation is what? An expression of the momentum, right? But what is momentum? Mass times velocity, right? So, if this is an expression of the momentum equation in the x direction, what is U? Velocity in what direction? X direction. Very good. So similarly, this is the V here is the velocity in the y direction, and W will be the velocity in the z direction. Okay? Now, in all these equations, the first term, which has to do with the rate of change, the partial rate of change of the velocity in the partial rate of change of the velocity, and of course, rate of change of velocity is what? Acceleration, right? So the first term represents local acceleration in the x, y, and z direction. These three terms that comes after the local acceleration are what we call the convective or convection terms. Okay, how the mass of the fluid is pushed, okay, within the pipe, for example, is convected within the pipe. Okay, convection is nothing but forcing a fluid to flow over a surface. And then we are saying that, well, the local acceleration and the convection of the fluid has to be balanced by the piezometric pressure gradient as well as the viscous terms or viscous forces acting on the object. Okay, we have a class?
Yes, some students have.
Oh, some students have class. Okay, so we've done 1 hour already. Mm-hmm. Right.
Some of you are leaving, others are also close to
Yeah. Okay. So let's give a pause for that interchange, and then if you have any questions, ask. Yes.
Then in terms of the notation, you have just U subscript X, U subscript Y, and U subscript Z for the different velocity in the different
Yes. So this would be, this U would be UX. Yeah. Okay. Well, okay, what happened? Well, you see, okay, so the velocity vector has 3 components. Okay, the velocity vector has 3 components: U, V, and W. So basically, that is your X, Y, and Z. So it's the decomposition of those components in the 3 directions of the momentum equations. Okay. Now, okay. So for those of you who are just walking in, we have started a discussion on what we mean by computational fluid dynamics. Okay, and we talked about how computational fluid dynamics can be applied across various spectrums of engineering applications, such as aerospace engineering, marine engineering, biomedical engineering, or biomedical application, environmental applications, and so on and so forth, okay? These notes would be available, so you can go back and review those applications. We also talked about what we mean by modeling, okay, which is basically the starting point of doing any CFD. Okay, if I want to do any CFD, I have to come up with my mathematical representation of the problem. Okay, and then a numerical solution of that mathematical representation of the problem. And of course, that mathematical implementation of the problem has to be cast in the form of an initial value problem. That is, it must have initial as well as boundary conditions. So when you were taking your differential equations or your calculus class, you see your professor will give you a differential equation, he will give you some boundary conditions and an initial condition, and he says solve it for the dependent variable, okay? So all that we are saying here now is that instead of your professor giving you those differential equations and the boundary and initial conditions, now you, the computational fluid dynamics scientists, have to come up with your model, your differential equation representation of the system, and then determine the boundary conditions for you to solve it. And so in this case, you know, all that I'm demonstrating here is one of the means of doing that is by coming up with, say, the Navier-Stokes equations, which is an expression of the momentum equation applied to a given fluid flow system, okay? And then we can also apply the continuity equation, which basically represents the conservation of mass applied to a given fluid flow system, okay? In applying the conservation of mass and also conservation of momentum, you may need the equation of state, okay? For example, in compressed flows, okay, you may need the equation of state to be able to cast the pressure in terms of the density, the ideal gas constant, and the temperature. Okay, or you may need, for example, this Rayleigh equation, and when we write the energy equation, you also need other equations such as Fourier's law, Fick's law for diffusion. Okay, you need all sorts of equations to fully capture or model your CFD problem. Any comments or questions? Okay, let's move on. So based on the physics of the fluid phenomena, CFD can be distinguished into different categories using different criteria. Okay, one, we are saying that, well, you know, why is all of this important in being able to distinguish between different criteria? You, the engineer, have to have that understanding, particularly when you are using different softwares, okay, to solve the problem. Okay? If I'm using an ANSYS Fluent or I'm using a COMSOL software, any CFD software that you can think of, or I am basically writing my own CFD, I'm doing my own CFD programming from scratch. After I have basically determined the mathematical formulation representing of the physical system, I need certain simplifications in order to solve the problem. Okay? Knowing those simplifications helps me to basically distinguish between the different categories or the criteria that has to be applied in the solution of that CFD problem. And so these are just examples of some of the simplifications or the criteria in classifying CFD problem. First here, we have to distinguish between whether we have viscous or inviscid. Okay? If it's viscous flow, then we don't have to worry about the viscous terms in, you see? If it's viscous flow, then we don't have to worry, then we have to take into consideration the viscosity in the momentum equation. But if we say, well, the problem is inviscid, we can neglect viscosity, then that means that this whole term can be dropped. Okay? The viscous forces can be dropped from the solution. If the problem is internal or external, remember the example that I gave, okay, where we're looking at, the release from the floodgates in a dam, okay? That is an open channel flow, okay? So we'll classify that as an external flow. But if the flow, or another example of external flow is the flow over an aircraft, okay, over the jet F-18 aircraft, or the flow over an automobile. Okay, those are all external flow. We are looking at the effects of the fluid flow over the structure in it. Okay, on the other hand, if it's an internal flow, that is the flow is within a confined, bounded region, then we have to classify it as such and solve for the flow inside the pipe or inside the tank. We have to also distinguish whether the flow is turbulent or laminar. Okay? The RE basically here represents the Reynolds number. Okay? You can use the Reynolds number, if you recall from your fluid mechanics, to classify whether we have turbulence or laminar. And so let me see if you remember the difference between laminar and turbulence for a pipe flow. What is the transition from laminar to turbulence in a pipe flow? What is that Reynolds number? 2,100, 2,300, okay? Very good, okay? So this is all we are saying here, okay? Quick back of the hand calculation in doing your analysis, you establish that, well, we don't have to worry about turbulence. We are just dealing with laminar streamline flow in the system, okay? So we have to decide that. We have to decide whether we have incompressible flow or we have compressible flow. Okay? In that case, the Mach number helps us determine whether we have incompressible flow or compressible flow. Okay? Do we have single or multi-phase flow? Okay? Do we have single or multi-phase flow? In that case, CA represents the cavitation within the system, within the pump. Okay, where single flow could be you have water and its vapor, or multi-phase. Multi-phase means you have water and its vapor, or single means that you just have just the water flowing in the system, or just liquid flowing in the system. Whereas multi-phase can be gas and liquid. Okay, and then we have to think of thermal and density effects. Okay, why is density effect associated with thermal. Let's get the students to give us an answer. Why do we associate density with thermal? Why is that important? What happens to warm air? It expands, it rises, right? Okay, so in a given problem, we have to know whether we have thermal implications, because those thermal implications tells us that we also have to consider conservation of energy within the system. Okay, so not only are we solving continuity, that is conservation of mass and the conservation of momentum, we also have to consider conservation of energy. Free flow and surface tension effects can also be important within a given system. Okay, the Freud and the wear number in terms of free flow and surface flow, and then the Peclet number in terms of chemical reactions and combustion. Okay, so and this is not the end of be all or end all of all of this. This is just saying that you have to clearly understand the category or the nature of the system that you are solving, so that you can use the proper formulations in the computational fluid dynamics. Okay, if the fluid is non-reacting, then of course you don't have to worry about chemical reaction and combustion. But if it's reacting, then you have to worry about chemical reactions. Then you have to introduce Fick's law and other laws into your governing equations. We continue with modeling now. We want to drill in particularly to initial conditions. The initial conditions basically impact your unsteady flow and your steady flow. Okay? The initial conditions should not affect your final steady results. Why is that? And your initial conditions only affect convergence path. Why is that? Your final steady result, basically, you are saying that for time into infinity, your environment remains static, constant. The conditions of your system does not change. Okay? So if the conditions of your system does not change, then it is steady state. Okay? You have a steady state process. Okay? But on the other hand, if your initial condition, okay, is going to impact your solution at every time step, then it leads to an unsteady flow problem. And so you have to pay attention to your initial conditions. Okay? And your initial conditions that you set also affects how your solution basically converges in terms of iterations. You see, when you start your computation, you don't smoothly arrive at steady state. Okay? It may take you some oscillations within your solution to arrive at your steady state. And so we say that your initial conditions needs to reach at a converged solution. So it is important how you basically select or specify your initial state of your system. Okay, and you have to basically develop the experience of coming up with reasonable guesses to speed up your convergence of your solution. Now this part here is understanding the numerics, okay, and basically understanding the numerical solution process and be able to make accurate prediction or guesses in terms of how to obtain a converged solutions. Now, for complicated and steady flow problems, CFD codes are really run in the steady mode for a few iterations for getting a better initial conditions. What this means is that, if I know that I'm going to have an unsteady problem, I'm solving an unsteady problem, the easiest solution is actually solving the steady state problem. Okay, assuming that your system stays the same at all times. So if you start with the steady state solutions, at least, let's say that I want to find the temperature of this room based on this air conditioning. What is the steady state temperature that I want to attain in this room? Well, if the steady state temperature, right now I'm looking at my AC, it says 19 degrees C. Okay, it says 19 degrees C. That means that I want the steady state temperature of this room to be 19 degrees C. But if the AC is turned off, because of the environmental conditions, this room is going to warm up, right? And so the temperature might be, let's say, around 22 degrees C. And so our initial temperature is actually 22 degrees C. Okay, that is our initial temperature. So if I'm modeling the process, then my initial temperature should be 22 degrees C. On the other hand, I know that if my final temperature is going to be 19 degrees C, then I shouldn't pick a very low temperature because that would lead to a lot of inconsistencies in my result. It won't allow me to reach at my steady state solutions quickly. Are you guys with me? Do you follow me? Okay. So let's look at this flow in a pipe. Okay. We can look at it from the three-dimensional view sense. Okay. You have flow entering here and flow leaving. And we can also look at it in a two-dimensional sense. Okay? By two-dimensional sense, I'm saying that, well, I know I have symmetry, right? So I have symmetry along the axis. Okay? And so if I have symmetry along the axis, that means that in the solution of this pipe flow, I can use an axis symmetric representation of the pipe and still get reasonable results. That saves computational time instead of solving the full three-dimensional problem. Okay? Because in the full three-dimensional problem, that means that I have to solve the full Navier-Stokes equation for momentum in all the three dimensions. Okay? Whereas in this case, I only have to worry about the axial and the radial dimensions. Okay? Now, what are the boundary conditions? Well, the boundary conditions that we normally consider in solving pipe flow is the no slip or slip-free on the walls. Okay? Periodic and inlet condition. What we mean by inlet condition? We have velocity inlet, mass flow inlet, constant pressure. And the outlet condition, we have constant pressure, velocity, convective, zero gradient. Now, let's see what we mean by these. This is the inlet, right? Likewise, in this axis symmetric representation, this is the inlet. So in the inlet, we are saying that the velocity in the x direction, u, is some constant value c. Okay? The velocity in the x direction, u, is fixed at some value c. However, there's no flow moving upward, right? At the inlet, the flow is just horizontal. The flow is being pumped into the pipe. And so then I know that the velocity in the y direction is 0. All right? At the inlet. At the outlet, I can fix a constant pressure at the outlet. Well, I can say that at the outlet, the pipe is exposed to atmospheric pressure. If the pipe is exposed to atmospheric pressure, well, then this P is equal to C, a constant is just atmospheric pressure. Okay? And then another boundary condition, because I've reduced this to an axisymmetric flow, that means that, you know, what happens on top is the same as what would happen on the bottom side. Okay? It's symmetrical. So then at the line of symmetry, the velocity is 0. Okay? Or the pressure gradient at the line of symmetry is 0. The rate of change of the velocity in the radial direction is also 0. Okay, yes? Okay, why is the velocity 0 at the line of symmetry? Basically, we are saying that the velocity inside the pipe, the velocity enters constant inside the pipe, okay? And if you were to draw the velocity profile, you know, particularly with no slip condition, you see that it will be somehow parabolic. Okay, it will be parabolic. I wish I had something to draw it. It will be parabolic, so we are saying that, you know, well, there will be variation of the velocity radially, but when you come to r is equal to 0, it is 0. Well, this is the v velocity, not u velocity. Okay? Inside the pipe, there is velocity variation in all directions. Okay? But the vertical component is 0. Okay? So that's a good question, good point. Okay? And similarly, the pressure gradient at that point is also 0. And you have rather to your point about the fact that we have to have maximum velocity in the axial direction. The u velocity has to be maximum. That is why du, dr is 0. Okay? All right. Any comments or questions? Now, in terms of selection of models, basically CFD codes typically designed for solving certain fluid phenomena by applying different models, okay? Again, we apply whether we are going to have viscous versus inviscid, turbulent or laminar. If you have turbulent flow, then you have to have a turbulent model. Okay, you have to have a turbulent model. Now the question is, why do we have to have a turbulent model? Well, let's go back to our Navier-Stokes equation. If you have turbulence, then that means that these velocities are fluctuating. Okay? They are not uniform. So the question is, well, if the velocities are fluctuating and are not uniform, then how do I capture accurately the velocity in my momentum equation. To accurately determine these viscous forces in my fluid. Okay? We have to come up with an appropriate turbulent representation. Okay? We have to come up with an appropriate turbulent representations. Now, that is an advanced subject. Okay? So for you undergraduates, I'm not going to bore you with that. In fact, in our fluid mechanics, we have to take a separate course in turbulence to actually derive the turbulence models that can be applied to a given problem. Okay? But there are various turbulence models that can be applied. And so, yes, we need to determine whether the flow is laminar or turbulence so that we can apply the right turbulence model. We need to determine whether the flow is incompressible or compressible so that we can apply, based on the Mach number, we can apply the equation of state or not. We need to apply, we need to know whether we have a single or multi-phase system so that we can apply the correct cavitation model or two-fluid model in the solution of the CFD. You know, when you go into a lot of these softwares, you see, there are basically panels within it that tells you that, look, if your solution, if you are solving an incompressible process, just turn on the incompressible model part of the model. Okay? If you don't turn on or turn off the appropriate model, then you're not going to get the right solution. So that is all this is saying. I have to have a clear understanding of the nature of my flow so that I can turn off or turn on the right model in order to get an accurate solution. Now, if you are, of course, deriving that from scratch and solving it on your own, then your derivation, of course, you are taking that into consideration. But, you know, if not, then to accurately produce correct simulation results, you have to have a clear understanding of the phenomenon that is taking place so that you turn on or off any of these modeling features, okay, within your CFD program. Comments or questions? Yes?
So basically, all these models are integrated in the required software.
Exactly. Okay? A very good CFD program, okay, a very good CFD program like ANSYS has all of these integrated within it. Now, not all of them do. Okay? In the case where they don't, then you, the expert user, have to basically do it by writing your own user-defined routine that would be linked to the solution process. Okay? That is another subject. We are not going to go there. Okay? But all I'm saying is that, you know, and at the back of your mind, in designing any CFD problem, you know, you have to have a clear understanding of the physics of the problem so that you can model it accurately. Any comments? Yes?
According to some form of velocity distribution model, like a model that tries to describe the velocity distribution.
Yes, your turbulence model basically describes the velocity model. And so, you know, some, you know, they call the large eddy simulation model. Some they call it Reynolds average, you know, kinetic energy epsilon model, and so forth. So it's basically a way of how the velocity is distributed. So now we understand how to model, okay? We've done all of that. Now we have to solve it, okay? So at this point, we just put on our thinking caps of what we learned in our numerical methods class, okay? In our numerical methods class, you know, We learned all sorts of numerical tricks, Newton, Ramson, Gauss-Seidel, we learned about the Jacobi matrix, and so on and so forth. Okay, that is what this is doing in the background. Okay, so here it says that the continuous initial boundary value problems are discretized into algebraic equations using numerical methods. And then after that, we assemble the system of algebraic equations and solve them to get approximate solution. We are solving, remember in numerical methods, you have your domain, you discretize it, okay? And so you are obtaining discrete solutions at different points within your computational domain, okay? Versus the exact solution, which is a continuous solution at every point. So here, as you can imagine, depending on your discretization method, that would impact your solution. Depending on what solver or what numerical parameters that you are specifying, that would impact your solution. Depending on how you are generating your grade, or if you are going to do any grade transformation, that would impact your solution. Depending on whether you're using high-performance computing and some post-processing application, that would impact your solution. Okay? Depending on if I'm solving the problem on my laptop, okay, versus I'm using a supercomputer with so many computing clusters put together to solve my problem, that impacts the solution. Okay, so we have to understand the numerical methods behind the solution process so that we can accurately specify the approach to solve it. And so what are some of these discretization methods? Okay, what are some of these discretization methods in CFD? Okay, let's look at them. One of the first or more simple applications, the discretization method in CFD is the finite difference formulation, the finite difference methods. It's very straightforward to apply, and it's usually applied to a regular rectangular grid with, let's say, the x interval the same as the y. Your delta x is equal to your delta y. Okay, that is basically your finite difference method. Versus your finite volume methods and your finite element method, which basically puts together irregular meshes, okay, irregular meshes to form your computational domain. Okay? And so really, in CFD, we can take a whole course on finite volume methods. We can even take a whole course on finite difference methods, and we can take a whole course based on finite element methods. Okay? What is the advantage of using one over the other? It all depends on the complexity of your problem. Okay? If it's simple geometry, then finite difference methods would basically be appropriate. If it's a more complicated structure, then it's best to use the finite volume or the finite element method. Finite element methods are more applicable to structural problems where you are determining stresses and strains within a structural material. Okay? Whereas in fluid flow systems, the impact of fluid forces or stresses on objects, you use either the finite difference or the finite volume approach. Each type of methods above use the same solution if the grid is fine solutions. Okay? In the limit as your delta x approaches 0, fine mesh, The limit as your delta y or your delta z approaches 0, again, yeah, that means there's the spatial discretization is very fine within the system. All these two methods collapse to the same solution. You're going to get the same results. However, like I said, some methods are more suitable to some cases than others. Finite different methods for spatial derivatives with different order of accuracies can be derived using the Taylor series expansions. Who remembers the Taylor series expansion? Thank you, Prof. Okay. The Taylor series expansion, hopefully, we'll see later on. I'll go over it in terms of helping you see the discretization using the Taylor series expansion. But suffice it to say that, depending on your finite difference solution, simulation will be accurate depending on your order of differentiation, okay? Such as whether you are using second order upwind scheme, you are using central differences, and so forth for the finite different methods. In general, higher order numerical methods usually predict higher order of accuracies. But here the problem is that they are basically unstable due to less numerical dissipation. Okay? What do we mean by temporal derivatives? Temporal derivatives are time-dependent derivatives. Okay? In your momentum equation, you have time-dependent derivatives. Or in general, if your problem is transient, that means that you cannot neglect the rate of change of the quantity with time. And so you have temporal derivatives. They can be integrated either by the explicit method, and these explicit methods are the Euler, Runge, Kutta, and the explicit methods, that is the beam warming methods, and so forth. I think in your numerical class, you must have talked about the explicit and implicit methods of solution of these numerical solutions. Okay? Any comments or questions? Okay, so this is just expressing how to discretize your differential equations. And by that, I go back to my Navier-Stokes equations, and I'm saying that, this term, this partial derivative has to be discretized. I can discretize it using finite difference representation, using finite volume representation, using finite element representation. Same for all these other terms. If I use a finite difference representation, for example, then I'll use a Taylor series representation. The Taylor series representation can be, for example, a forward difference, okay, a backward difference, or a central difference. And I'm saying this without writing it, so it may not sink in. Later on, I will demonstrate that, okay? So all these has to be discretized. The discretization results in a set of algebraic equations that you have to solve. Okay, so that is what we are talking about. Now, if you are discretizing using an explicit method, okay, we are saying that explicit methods can be easily applied but yield conditional stable finite difference equations which are restricted by time steps. Okay? What we mean is that you have to be careful in using an explicit method because it only gives you a conditional stability. if you use a large time step, okay, let's say that you are solving your problem for 1 hour. Well, in my solution, my delta t could be 1 second or 1 minute, or maybe even 5 seconds or 5 minutes. Depending on what you set as your time step, that would impact the explicit solution. It gives you a conditional stability. Your solution is not stable. If your solution is not stable, that means that your solution is not going to converge and you're not going to get a solution. You're wasting your time. All right? On the other hand, implicit methods are unconditionally stable, but needs efforts on efficiency. So implicit methods of discretization does not have the problem with time step. Okay? You can set your time step as small as you want or as large as you want, and you're okay, but it affects efficiency. So remember, if I set my time step at 1 second versus 5 minutes, in terms of computational time, which one do you think is longer? A delta t of 1 second or a delta t of 5 minutes? Which one is longer? A delta t of 1 second in terms of how long it's going to take you to get your final result. If your delta t is 1 second versus a delta t of 5 minutes, which one is longer? 1 second is longer, because that means that for each 1 second, you are calculating a solution of for each 1 second, you are solving the complete set of your algebraic equation. Okay, so, if you are solving it for 1 hour, how many seconds do you have to solve it? That is 600, right? Now, versus 5 minutes, then you're using a larger delta t, so it solves a shorter time, but then, there'll be differences in terms of the accuracy of the solution, but it's conditionally stable. Okay, that is what we mean by this. Okay? Now, usually, higher order temporal discretization is used when the spatial discretization is also of higher order. Okay? In terms of stability, a discretization method is said to be stable if it does not magnify the errors that appear in the course of numerical solution. What does this mean? In other words, if I'm solving the problem using explicit method, and I am restricted by the time step, if I don't select the correct time step, then that means that it's going to magnify the error in my solution. Okay? It's going to magnify the error in my solution, and I will not get the right results. Okay? So your solution will not be stable. Okay? Will not converge with time. Okay? So that is what this is saying. Yes? A smaller time step should yield a better accuracy than a larger time step. That is the ideal case. Now, the penalty is the computational time or your computational resources. If you have a very huge computing system with a large storage space, then you can afford to do that. Okay? If you have a supercomputer, then you can afford to do that. Now, preconditioning method is used when the matrix of the linear algebraic system is ill-posed, such as multi-phase flows, and flows with a broad range of Mach numbers. Okay, so when you assemble your matrix for the discretized domain, you can end up with an ill-posed matrix. Okay, some matrices are so nice, so beautiful that you can use a standard algorithm. Okay, such as the Thomas algorithm, which is a tri-diagonal matrix solver to quickly solve the problem. But if it's such that you don't have a well-structured matrix, then you have to do some preconditioning, okay? And that is a numerical trip that you have to do. And here it's saying that this preconditioning is required particularly when you have multi-phase flows and when you have some problems that are compressible because of huge Mach numbers. How do we define Mach numbers? Yes. Thank you. All right. So I'm just seeing whether I'm saying some terms and whether you relate. Selection of discretized methods should consider efficiency, accuracy, special requirements such as is going to flow like a nozzle. Okay? In a rocket nozzle, the fluid is going to flow through an inlet with a diffuser at the outlet. Okay? Well, in order to analyze the flow within the nozzle, we have to construct our grades. Note that, you see, since this is not a straight line, if this was a straight line, then we can easily construct this equally spaced grade with the same delta x as delta y. Okay? Delta x is the distance from this point to that point, and delta y is the distance from here to there. Okay? So we can really get the same delta x and delta y. But because of the curved nature of the outline outside of the flow channel, we cannot easily get this. We can only get this form of equal distribution of grade if we transform the y coordinates to the y-x coordinate to this new coordinate system. Okay, eta and psi. Okay, so we have to do a coordinate transformation. This is the physical domain, and this is now the computational domain. So we do the transformation between the physical domain and the computational domains by basically doing this transformation using these partial derivatives. To do this transformation, that means that you have to know the equation that represents this curve. Okay, this curve is a function that is varying depending on x with y as your dependent variable. So I'm saying that if I take that function and take the derivative of f with respect to psi here, and psi with respect to x, and f with respect to eta, and eta with respect to x, you can obtain a transformation of this grade to that. And we do the same for the y direction. Okay? So, yes?
Because you want the structured grade.
Because I want a structured grade, yes.
These are the points of calculation.
Grid points are the points of calculations, but your computational domain has to be gridded, right? So we are saying that, well, you know, this is not a uniform outer layer, okay? So in order to get to this computational domain, we have to do some form of a grid transformation. Otherwise, the other approach would be say, well, remember, if I cannot use a structured grid, I can use an unstructured using a finite volume or finite element. Okay, so yes, I don't have to do this transformation, but I can use a finite volume or a finite element to solve the problem. Yes?
So in that case, with the computational domain, will that one have a kind of higher accuracy than the one using the finite kind of computation? If you are looking at the two, which one will have a higher accuracy?
Okay, so the question is, once you do this transformation, will your results be the same in terms of accuracy? And the answer is yes, because once you obtain the result in this domain, you have to transfer back to your original domain. Okay? Yes, every point in here will map into a point over here. Okay? And of course, the numerical accuracy basically depends on how well you do this mapping. Okay? But the results from here can be mapped back into your actual physical domain. So, you know, we are able to use numerical methods to solve our problem, playing all sorts of tricks with our grades. Now we get some results. So even the results give us wahala. How do I depict my results to clearly understand, what I'm seeing? Okay? And so, yes, there are post-processing softwares that you can use to even represent your result. You see, this figure is an isosurface of Q300 color scheme piezometric pressure. In other words, it's a surface showing the pressures at various locations. Okay, showing pressure at various locations. Now, this is two forms of representation. Okay? This form is more enhanced than that. So here, in this enhanced form, at the wake here, you can see clearly, some of the pressures in the different regions. Let's say assuming that the darker regions means the higher pressure region. Okay, over here, you cannot see the pressure gradients clearly, right? Because all of them look red. But whereas if you use this more enhanced post-processing system, you can see the pressure regions a bit more. Okay, and so yes, you can visualize CFD results. That is whether it's contour, velocity vectors, streamlines, path lines, streak lines, and isosurface in 3D and so forth. And you can use a CFD user analysis, verification and validation data to further analyze your results through post-processing, commercial softwares. Okay, those are available for you to analyze. Well, so far to this point, I've introduced you to the CFD process, okay? From us talking about what is CFD, examples of CFD, and how we start modeling from the conservation equations. Once we've obtained the conservation equations with the boundary conditions, we've looked at how to potentially discretize them based on the appropriate geometry and coordinate system, and using well-known or some discretization technique. All of this have been integrated into different commercial CFD codes. Okay, commercial means companies have developed these softwares that they charge us a lot of money to use in order to access the license files. So whether it's Fluent, ANSYS Fluent, okay, for example, Fluent started out being a software on its own for purely CFD analysis, and then ANSYS bought out Fluent, okay, and integrated it into its structural analysis system. So if you go into the ANSYS, you have the fluid flow analysis part, which is Fluent, and then you have the structural analysis part within it, okay? So you have all these different softwares. Some of them are more for research, okay, such as the CFD SHIP. Some are public domain. In other words, if you go online and Google, you can have public domain CFD softwares that you can use. Okay, you just have to understand the input and the output, okay, and how to put in your properties and so forth and be able to use it. And then even in doing your CFDs, there are grid generation softwares, okay? A long time ago, in order to do Fluent, you needed the grid generation gambit, okay, to be able to generate your grid before you did your computations in Fluent. Others, grid generation is the flow visualization software, TechPlot, FieldView, and so forth. So all these software, COMSOL, ANSYS, CD, Adapco, the GridGen, and so Phoenix, all these are available softwares for CFD analysis. Knowing that we have these softwares for CFD analysis, then of course, now what is, we have to get the CFD process in mind, okay? I have this challenge that I want to solve. I don't want to, my company cannot afford doing the experiment, okay? Maybe my advanced calculus, advanced differential equation solver, derivation skills are not that strong for me to derive a complete set of equations. And then even when I derive a complete set of equations, I may still need a computer to solve it, which is still complicated. So why don't I use CFD? Well, so what is the process of using CFD to solve a problem? Okay, so the purposes of CFD codes will be different for different applications, all right? Investigation of bubble fluid interactions for bubble flows, study of wave-induced massively separated flows, free surface flows, etc. So depending on the problem, okay, the application of the CFD code is different, okay? Depending on the specific purpose and the flow conditions of the problem, different CFD codes can be chosen for different applications, for aerospace, marine, combustion, multi-phase, and also flows. Once the purposes and the CFD codes chosen, okay, the CFD process is the step to set up the initial boundary value process and run the code. What is the first step? You have to know your geometry. Okay? How do I capture the geometry? We've already talked about capturing your geometry by either drawing it using a CAD, computer-aided software. If it's very complicated and I cannot draw it using a computer-aided software, now there are 3D scanners. Okay? There are 3D scanners that you can 3D scan it and obtain a digital image that you can import into your software, okay? So that is how you create the geometry. You have to know the physics. Yes? Yes.
Some gas in the glass breaks physical pieces.
Mm-hmm.
Yeah,
okay.
Something I imagine.
Okay, that's a very good point. You see, this first geometry has a lot of implications. How do you determine the control volume that you are going to do your computation in? It goes back to our problem for our aerosol dispersion research. Okay, I want to look at the dispersion of NOx in the whole of Kumasi. How do I do that? Okay, or in the example that you gave, the glass is going to break up and be dispersed. How do you do that? Well, you do that by defining an area, by defining a control volume. So that control volume could just be a rectangular enclosure. Okay, that control volume could be a cylindrical enclosure. Okay, that control volume, if you are looking at the aerodynamics over the Earth, which is spherical, could be a spherical enclosure. or a spherical surface. Okay, so this geometry basically saying that, pay attention to the system that you want to analyze and come up with the appropriate geometry to use in doing your analysis. Once you have achieved that first step, then the next step is the physics. What are the conservation equations that you want to solve? Okay, if I go into any of these software, I have to tell the software, solve the conservation of mass. So I check the icon or the panel within that software that says that, okay, these are the conservation equations that I want to solve. Conservation of mass, conservation of momentum, conservation of energy, conservation of species. Okay? So I have to specify the physics. I have to discretize my geometry. I'm going to look at flow on the outside of the airfoil or flow within a pipe. Okay, so you have to discretize it. Okay, then you have to solve it, and you have to prepare reports that you'll be sending to your chief engineer or your supervisor or, your funding agency for the project to give them your results. Okay, and basically you do the post-processing part also in this scheme. Yes. Which one is difficult to deal with? Well, let's delve into it over here. Okay, so you see that the geometry involves what? So it doesn't have the properties of the fluid. That means you have to get it from somewhere to integrate it to the software. That means that you have to write a user-defined script that will effectively integrate the properties that you are getting from another database to the system in order to solve it. Is the flow viscous or inviscid? What are your boundary conditions? What are your initial conditions? Okay, so you see that the physics can be very engaging. Okay, yes?
Sometimes, simpler models, solve first, and the solution you use as starting point for. So, like a good example, we can use of state. Maybe you first use ideal gas to get some temperatures and whatever.
Very good. That's a good point. Yes, we do that. Okay, we do that. Another case in point is, properties are temperature dependent. Let's solve the problem for constant temperature and get a baseline. And then let's throw in more complexities to see how your system will change if the temperature changes when you include the nonlinearities. Or let's first solve the simple laminar flow problem before we make it more complicated with turbulent flow. Okay? So really, in the physics, that's where you're making these assumptions. Okay? It's nothing but making assumptions. Now, so even though I'm saying that, to your point, the problem can be very complicated, however, I can simplify it for myself depending on the assumptions that I'm making here. Okay, for the physics. For the meshing part, I'm stuck as to whether it's unstructured or it is structured. In my software, do I have an automatic system for generating it, or do I have to input some transformations in order to generate my mesh? Similarly to the structured mesh. in solving, am I solving a problem as a steady or unsteady? Okay. How many iterations do I want to solve? Okay. What is my convergence limit? How precise do I want my answers, my solution? Okay, and what numerical solution scheme am I going to use? A tri-diagonal or pentadiagonal system or what? In terms of reports, okay, what do I want in terms of my output? Am I looking for lift, drag, velocity, or what? Or temperature? What type of reports do I want? Okay, do I just want an XY plot? Do I want a contour plot? Okay, now these two parts, you know, I tell all my graduate students that don't give me any CFD solution when you haven't verified it and you haven't validated it. Okay, and so you may ask, how do I verify or how do I validate? Well, again, it goes to your point, Prof, where instead of solving the complete problem, maybe I'm going to solve it for a simple problem with known exact solution or with known experimental solution. Once I know that, hey, my solution works and I can apply it to this different system, then I go for it. Okay? So I've verified and I've validated. Yes?
Balance. So you've done some, let's say it's a reactive system.
Yes.
So you've done all this simulation. But they should base on alcohol atomic balance, maybe from it's gasification, let's say. The carbon in the fish should be equal to all the carbon that is. Is that verification?
Yes, that is part of the verification. Okay. Or another way of putting it is, okay, it's energy conservation, right? So there has to be an energy balance. Okay, so if you are not getting your energy or your atomic balance verification, then that means that it has to obey the first law. Okay, it has to obey the first law, it has to obey the laws of physics. Okay, and even in terms of verification, another verification that is important is what I call grid optimization. Okay? The solution that you get from a sparse grid. Okay? I talked about, using a solution for 1 second versus 5 seconds. We know that the 1 second will give me a long time, but will give me a more accurate result. Similarly, a fine grid of a delta X, very small, and a delta Y, very small, will give me a more refined solution, a more accurate solution than using a large delta X and a large delta Y. Okay, so what I ask my students to do will be to do a grid optimization. First, do the experiment or the simulation with a coarse grid, a medium coarse, and a fine mesh. Let's see the results of these three cases. If it converges, if you see that as you keep reducing the grades, it is converging, then you know that you are in the right direction. And then the ultimate question is, well, what is my computational penalty in terms of resource and in terms of my accuracy desired? Do I want to spend all the time using the fine grid, or is the solution from the medium coarse grid close enough to the fine grid to use? Okay, and the final part, the post-processing, what type of contours, what type of vectors, what type of streamlines. This is just a little bit more detail in terms of the geometry, select geometry parameters and domain size. Selection of an appropriate coordinate system. Remember I said rectangular, cylindrical or spherical. Determine the domain size and shape. Are we going to do the analysis over the whole of Kumasi or just KNUST? Okay, in terms of size and shape. Make appropriate simplifications. What kinds of shape needed to be used to best resolve the geometry, lines, circles, ovals, etc. For the commercial code, the geometry is usually created using the commercial software, either separated from the commercial code itself, like Gambit in Fluent, or the design modeler in SpaceClaim. Okay? For the physics, flow conditions and fluid properties, the flow conditions, is it inviscid, that is no viscosity or viscous? Is it laminar or is it turbulent? Is it isothermal or there's a temperature dependence? Fluid property. What are the fluid properties needed for the solution? Do I need density? Do I need viscosity? Do I have thermal conductivity and so forth? Okay? Flow conditions and properties usually presented in dimensional form in industrial commercial CFD software, whereas in non-dimensional variables for research codes. Okay, what is the difference? I'll talk about non-dimensionalization versus dimensional. There are some cases where, because of research, I want to non-dimensionalize my solution so that I can analyze my system for a whole range, okay, or for I can transfer my solutions to different domains. And so for research-wise, it's best to do dimensional analysis, okay? The selection of models, different models usually fixed by codes, options for user to be chosen. And then the initial and boundary conditions not fixed by codes, user needs to specify them for different applications. So Ms. Lydia and Professor, Doc, I need your properties, okay? I need your time-dependent properties for our analysis. Yeah. In terms of meshes should be well designed to resolve important flow features, which are dependent upon the flow conditions, e.g. the Reynolds number, such as grid refinement inside the wall boundary, okay? Wall boundary layer, okay? And let me just go back, bear with me as I go back and to this figure. You see, if I'm doing flow over an aircraft's wing, okay, this is an aircraft's wing, I need fine mesh resolution around the airfoil because of the boundary layer basically contain or can capture the importance of the forces acting on the airfoil. Far away above the airfoil, it's not that important, okay? What happens with the airflow on the airfoil as the plane is flying at a given angle of attack? How does that affect the turbulence of the aircraft? Okay, so you need a fine mesh around the wing to be able to capture all those complexities. So yes, there are commercial codes for generating these meshes. The mesh together with the boundary conditions need to be exported from the commercial software in certain format that can be recognized by the research CFD code or other commercial codes. That is something that we have to contend with, okay? When you're using two different systems, they will not talk to each other until you put it in the form that they would understand, Okay, and in the solution phase, you set up appropriate numerical parameters, choose appropriate solvers, solution procedure, solve the momentum, pressure, Poisson equations, get the flow quantities, velocity, turbulence, intensity, and so on and so forth. Okay, that is the solve part. In the reports, well, what do I want to report? Okay, reports say the time history of the residuals, of the velocity, the pressure, and so forth. The reports report the integral quantities such as total pressure, friction factor, drag coefficient, and so forth. XY plots could represent the center line velocity, pressure distribution, friction factor distribution, and so forth. Other data that can be imported and put on top of an XY plot for validation. Okay. In other words, what report do you need from your analysis? Okay. It's not only pressure, it could be temperature, it could be species concentration. Okay. You have to specify that for the report to be generated. For post-processing analysis, you have analysis and visualization, calculation of derived variables such as vorticity, wall shear stresses, calculation of integral parameters, forces and moments, visualization, usually with commercial software, simple 2D contours, 3D isosurface plots, vector plots and streamlines, and animations. There are various special software such as this Amtech that can give you that capability for generating nice plots for presentation, post-processing plots for presentation. Okay, this is just an example of the software Flow Lab. Okay, and here showing the operation panels that would allow you to create a mesh for this enclosure. Okay, and the enclosure will be the area around the airfoil. Okay, this is basically your airfoil or cross-section of a wing. Okay, and so within this CFD software, you see that in the mesh generation panel, you specify whether you want structured or unstructured. Do you want automatic or you want to manually enter your grid generation information? That means that manual means you're going to specify your delta X, you're going to specify your delta Y, that is your desired, okay? And then you want to specify your mesh density and so forth. Okay, so each CFD software, has its own, icon panels for the various phases of the implementation. In terms of the solving process, this is the solve panel, and you see that in the solution, you want to capture the residuals versus the iteration. Okay. Again, in the solver, am I solving a steady state problem or unsteady problem? The steady state will be, that means that your solution does not depend on time, okay, versus unsteady where the solution depends on time. So you have to select what you need, and you have to specify the number of iterations. Okay, so here 1,000 was selected. Convergence limit, okay, 0.001 is your convergence limit. Precision, single or double, you specify that. And then numerical scheme, you also selected here is a second order numerical scheme versus first order numerical scheme, and so on. Okay, so this is the process solve panel And this is what you would expect to see in terms of the residual plots as the solution goes on. In terms of post-processing, so you go into the post-processing panel for flow lab. Again, you can specify in these regions what you want to look at in terms of the results, whether you want to see contours or you want to see vectors. Okay? These arrows above the airfoil are showing vectors of the velocity around the airfoil, whereas you have the contours in this case. And then here, this is showing the streamlines, okay, around the airfoil. Okay, again, you specify the type of results you want to see. All right, how much time have we spent? It leaves us just about 20 minutes. 15 minutes, okay. I open it up with 2 questions at this time. You see, I've gone through the whole CFD process in this lecture. Next time, we'll go into how to drill in and look at, okay, so behind all these solve operations, okay, what is the conservation equation looks like and where does it come from? We'll do some derivations next time. Okay, but I open it up for any questions. Yes?
For example, the residuals, how much is acceptable? What residual value might be acceptable?
Okay, so we look at the residuals, and the question is, what is acceptable? If I see that the trend is towards reduction of the residual, okay, then it's with time, then I know that it's acceptable. Okay, and basically, you basically indicate that you want your convergence within a certain value, right? So if I look at the residuals in terms of its conversion value, am I attaining the convergence criteria with each step of the iteration? When you see oscillating, then you know that your solution is no good. So maybe you need to tweak something in your solution. Have I motivated you to think of using CFD to solve a problem or pursuing further studies in CFD?
So that you might have to, do something to get the geometry first. So if you're going to design a reactor, you might first have to use some other technique to get the geometry before CFD can come in.
You have to basically create your geometry first, okay? And so depending on the complication, the system, maybe I'll neglect other areas of the reactor and focus on a given part of it. And so my CFD analysis will be just on that part, okay? I can choose to look at the whole automobile where I'm looking at the aerodynamics around it, or I'm just looking at the combustion chamber, okay? Or I'm looking at the radiator, okay? What part of the system do I want to look at? What is more important? Okay, you, the designer, have to look at it and design that accordingly. And remember, I said that CFD can be used for analysis and design. Okay. Hopefully, I'll present a case study where we are using CFD basically to design a cloud formation chamber. Okay, we are designing a CFD to design a cloud formation and environmental chamber that would be used to analyze the impact of aerosol nucleation and coagulation in the formation of clouds on different planetary bodies. Okay, in doing that, we look at different case studies. Well, what if we don't have any introduction of particles of aerosols within the system? Okay, so we don't have any velocity inflow, but we are looking at what is the presence of gases within the chamber, and then there's no flow into it. That can be just one step. And then we throw in more complexities and say that let us have inflow of particles, aerosols, into the chamber. Okay, that can be another extension of it. Now, okay, let's vary the temperature variation to some other level. Okay, the complexities can be built up as you go along. Comments or questions? Yes. That's a good question. Look, I'm not good at CAD. Okay? Somebody is going to generate a CAD model for me to import to do my work. You don't have to be the expert of everything. Okay? Or like I said, now we have 3D scanner. I have a scanner that can scan my whole body. Okay? Or for doctors in the biomedical field, they can basically scan the heart, a human organ, so that they can do their analysis on the organ or tissue. Yes. Okay, so if you're doing a complex geometry and your system cannot handle that big complex system, yes, you start with a small system, a scaled down version. It's almost like when you're designing and you're building prototype, you're not going to right away build the complete system, right? You're going to do a prototype and see what happens. And a case in point is in fluid flow experiment, in doing wind tunnel experiment. Wind tunnel experiments are not always done on full-scale objects. Okay, they do a prototype, a scaled-down model to do their experiment on it before, and then transfer the results to the full-scale model. So that's another way of looking at it. Yes. How do I do the verification? That's a very good point. And so in doing CFD-related research, okay, or in doing any research for that matter, okay, look, why reinvent the wheel when somebody has already done something? Okay? I mean, that is why as researchers we do a literature review, okay, to find out what others have done in the field. And so, our work may be just either tweaking or making a modification of their system or applying it into a different domain. So if I can repeat their work and make sure it works, then I can now apply it to my system. Does that answer your question? Okay. So there are so many ways of verifying work that has been done. Okay. And in the example that I'll show at the end, the case studies that I'll show at the end, yes, my students would take work that have been done in the field to validate their work before actually doing what we call parametric studies on their work. Yes?
I read that some CFD modules have inbuilt geometries. Does ANSYS have the same thing?
ANSYS has an inbuilt geometry, yeah, geometric solver. In fact, one of the things that happened, you see, Fluent, that is the CFD part of ANSYS, basically had two systems. They had Gambit and the CFD solver, okay? So you had to do your geometry in Gambit and then transport it into Fluent. Now, with the purchase of ANSYS by Fluent, ANSYS has already its grid generation system. So it was just a matter of integrating the ANSYS grid generation system or geometry generation system with the Fluent solver, all in one place. Comments or questions? Yes.
And later, wait for experiment to catch up. I got out to get this here. That physical, I'm saying, physics and like Einstein does some calculations. And on that time, there was no validation. Then later, the experiments catch up.
Yes. Yes, we are allowed to do that. And a case in point is the design of our aero cloud formation chamber that I'm talking about. This is something that is being designed, okay? We are using CFD to inform the design. When the system is actually built, now they are going to do the experiment. Okay? We are hoping that, our analysis and design works the way we want it, but when they do the actual experiment, there may be some tweaking, closing of the loop that has to occur. You had another follow-up? Well, if there are no more questions, thank you for your attention and engaging me. And we will continue with additional information on this topic.
Tomorrow.
Yeah.
Do the slides.
Yes, I'll forward the slides. I'll make the slides available. Good. Oh, yeah, okay, yes, okay, yes, I would like to take a group picture.
Yeah, because of the proper. In that case, I think the lights. The lights. Yeah, there's a force on that light. Oh, the lights. Yeah. I'll show it outside. Yeah, outside.
No, not 9. No, no. I have to see the VC. It's tomorrow afternoon.
Tomorrow at 12.
How about, is 1 o'clock okay for you, or?
One is fine.
1 is fine.
Yeah, 1 is fine.
1 is fine, yeah. Yeah.
I think we wanted to find out. So if now the ANSYS has the geometric component in terms of generating our 3D model.
Okay.
Because we've been trying to get some assistance with the planning.
Answers? Okay, sorry.
For that data